Come on in. Hey there, everybody. I want to tell you a little bit about my work today. And what I do is design technologies for emerging markets. And what I think is exciting about this is that we can use the constraints of those markets to drive innovation and create high-performance, low-cost solutions that work worldwide. So you're going to hear a little bit about our solar-powered desalination technology a little later in the talk. But first, I want to consider, why would you think about design in emerging markets specifically? Well, if you look at a lot of indicators for human health and well-being, things like clean water and sanitation and maternal health, a lot of the problems that are indicated by things like the UN Sustainable Development Goals, a lot of these challenges are by and large solved in countries like the United States, but they persist and affect billions of people in poor countries. And I think the reason is, if you think about the technologies we have in this country, you can adapt those, adding features, removing features, to move up and down a price and performance curve. But the problem is that in the developing world, people still demand a pretty high performance in what they want in their products. But the price point may be fundamentally different than what we pay for those same solutions in wealthy countries. And when you find yourself in a disparity like this, there's no way to adapt your way down that existing technology curve to get to that intersection point. You have to jump off it. You have to create disruptive innovations. And so what my research group does is we try to understand the unique physics and engineering and socioeconomic aspects of emerging markets to give us insights of how we can make that disruptive leap. And once we do make that leap, that's exciting because we can envision a whole new technology curve that grows out of that point. We can understand price points of wealthy markets, and we can create a whole family of solutions that serves rich and poor markets alike. And we call this process in my group engineering global development. And this is what we apply to every one of our research projects. So I want to put you in a mental context of what we have to do. This is a picture taken in a village in India where we're talking to farmers and talking to village people who have to drink and use salty groundwater. And this is what collecting data looks like for us. Right? It's not just cranking out equations on a whiteboard. It's collecting feedback and collecting knowledge that there's no way that a big white guy who grew up in New Hampshire would understand. Right? We have to work with people who understand their own local context and add information to the problem that's as valuable or more sometimes than the information that we bring to the problem. So with this understanding, we can understand concerns like drinking salty water gives me kidney stones, and maybe we can get an understanding of how much people would pay for a clean water solution. So we have to combine that on-the-ground work with some good detective work. So in our desalination project, we had to understand that the most prevalent contaminant of water in India is salt. And 60% of the land area in the country has salty enough water that you can actually taste it. And who this affects is at minimum, a quarter of India's population, which lives in villages of 2,000 to 5,000 people. So this gives us an idea of our target users, and it also told us that most of these people live off the grid, and so we'd have to make a solar-powered solution. We have to combine that with hardcore engineering science. So we had to dive in and understand the physics and energetics and thermodynamics of different desalination technologies. And the two big candidates are reverse osmosis, which I suspect many of you have heard of. That's kind of the industry standard. And a much lesser known and lesser used technology called electrodialysis. And what came out of this detective work is we realized that for the level of saltiness, for the salinity of what you find in India, electrodialysis requires only half the energy compared to reverse osmosis. That cuts the capital cost of your solar panel system in half. Furthermore, India is really water stressed. And in the next 10 years, it's projected that the consumption rate of fresh water will actually exceed the replenishment rate. And so with electrodialysis, we realized that we only waste 5 to 10% of the water that comes into the system rather than about 60% with reverse osmosis. So we combine all these insights together, and it gave us a roadmap of how we could actually design village-scale, solar-powered desalination systems. And serendipitously, a year ago, USAID was running a prize to make these type of systems, and we competed with over 60 teams from around the world, and the top 5 made full-scale systems, tested them out in New Mexico, and we ended up winning, because we were the only team that could produce the quantity and quality of water demanded by the requirements. And so since then, USAID's been pushing us to get this technology out to people and get them using it. So just this last January, we fired up our first pilot system in India. And through this process and through getting pushed by USAID, we're seeing that we have global opportunities for this technology. We're seeing that, yes, in village areas, we can provide clean water cheaply with solar power. Within this year, we're going to set up 4 test systems, one of which is going to be in Gaza. And now we're working with UNICEF on that. We're also seeing, by working with one of our partners, which is a big infrastructure company in India, that we could use this technology for apartment buildings and put a system on top and desalinate the water for everybody inside the building. We've also seen that we could replace home use systems that currently waste a lot of water using reverse osmosis and instead switch to electrodialysis. And we're seeing in the future that because we've done the rigorous engineering to understand how we can tweak this technology, we could tune it for situations like disaster response or military applications where you have to make a system that has no batteries so you can put it on a plane and airship it fast anywhere throughout the world. So to wrap up, I think this idea of engineering global development is really powerful. It led us first to understanding the unique socioeconomics and technical factors to see the disruptive opportunity for solar-powered desalination. We're using the same process in a bunch of other projects in my group, like prosthetic limbs, where we can tune the mechanical design of the limb to get the right biomechanical performance to get people to walk normally. We're also using it in drip irrigation, where we figured out some tricks to cut the pumping power of off-grid drip irrigation by half, which cuts the capital cost in half and makes solar-powered systems much more viable. And even for farmers on-grid, like those in California, it cuts their energy cost in half. And then finally, we've actually reverse innovated a product, which is called the Freedom Chair, where now we make a version of this wheelchair in India, which serves the developing world, and a version in Boston that serves wealthy markets like the US and Europe. So I think what's so powerful about this is if we look at emerging market challenges and use their constraints to drive innovation, we can use this process of engineering for global development to both create solutions that positively impact people's lives in poor countries, while at the same time creating high-value, low-cost products that all of us in this country could enjoy as well. Thank you very much.